Hello, everyone, and welcome to today's webinar on full circuit breaker testing with full demonstration. My name is Sausan Adnan, and I will be hosting this session today. Speaker for today's session is Mr. Ali Hussein, who is an application engineer at Megger Middle East. Also on the panelist, we have application engineers, Mr. Hamid Shahab and Ali Azam from Megger Middle East. Before handing the mic over to Mr. Ali, I would like to highlight a few points. First of all, you are all muted to avoid any disturbance during the presentation. Do park any questions you may have for the Q&A session at the end or share it in the chat window. All questions will be answered at the end of the session. Please make sure to follow our social media accounts to get the latest updates. The recordings will be sent to you within 2 days through the WebEx system as a standard process. Also, there is a small survey form at the end of the webinar, so please do fill the same for the feedback regarding the webinar. I now hand over the control to Mr. Ali. So let's get started. Over to you, sir.
Hello, everyone, and welcome. Good morning, good afternoon, good evening, wherever you are. My name is Ali Hussein, and today I will be your presenter slash trainer for this session. And we got quite a lot of things to do today, actually. Our agenda is packed with many things that I would like to talk about regarding circuit breaker testing. First, I would like to thanks to Mr. Hamid and Ali Azam for joining me today in this session. They will be helping me in answering some of the questions that will be asked by you guys. So without further ado, we will start first by explaining our agenda for today. First, I will give a quick introduction on medium voltage and high voltage circuit breakers. For example, I will talk about circuit breaker components, what type of tests that we do, and then we will start doing some tests, for example, contact resistance test, contact timing, minimum voltage pickup test, contact travel, and last, coil current trace, or what we basically call it coil current test. Because of the long duration of this session, today we will have multiple breaks in the middle, break 1 and break 2, after finishing some part of our agenda today. So I hope everyone enjoy this and learn from it. So we'll start first with an introduction to circuit breakers. When I give an introduction to circuit breaker, from our point of view as a test solution provider or power system testing solution providers, we divide circuit breakers into two parts. First, we have low voltage circuit breaker, which is usually below 1000 volt or 1 kV. And this circuit breaker will usually contain their own protection system included in them. So when we do, for example, timing test on this circuit breaker, we usually use primary injection or primary current injection method to test these breakers for all their parts, the protection and the mechanical parts or mechanism, interrupters, etc., etc. For medium voltage or high voltage circuit breaker, which by standard definition is more than 1 kV, and I believe in IEC standard, it's no longer called medium and high voltage, they just called high voltage. In IEEE market, they are still having this, I would say, standardization of medium to high voltage circuit breakers. Usually, these kind of breakers, they don't have their own trip. They cannot trip on their own. They need an external signal trip, either from, for example, control systems or from protection relays. So testing for these kind of breakers is usually done using circuit breaker analyzers. And there are many tests to these circuit breakers, but usually these tests will be focused on the mechanical parts and maybe the insulation of these circuit breakers. As the protection and measuring instrument transformers, they will be tested on their own separately. So for today's session, we will be mainly focusing on the medium and high voltage circuit breakers. So from now on, all what I am going to explain is based on these circuit breakers. So when I say medium voltage and high voltage circuit breaker, what do I exactly mean? There are many types, voltage levels, technologies used for this circuit breaker. Starting with the first picture I'm showing here, this is a medium voltage vacuum circuit breaker, where the interrupters of the circuit breaker is placed in a vacuum bottle or vacuum enclosure, and the measurement or current interruption is made by this vacuum. They are heavily or mostly used in distribution systems up to 50 kV because of their low maintenance requirement and cheap design. Then we have the transmission part, or I would say some obsolete parts of the transmission, which is oil circuit breakers. They are still available in some parts or some countries since they have been obsolete since a long time ago. Any kind of these circuit breakers is usually being decommissioned or being replaced by the newer technologies that is being dominating, which is SF6 circuit breakers. These SF6 circuit breakers usually comes either as a live tank or a dead tank. The breaker on the left here is a live tank circuit breaker, where the interrupter section of it is live. So any maintenance job for it, you require you to do a lot of isolation. Even if you want to clean the circuit breaker, you cannot do that since the body itself is live and have safety hazards. As for the dead tank type circuit breaker, SF6 circuit breakers, they not only for SF6, but sometimes also you can find it for other technologies. But the dead tank is usually something allow you, for example, to do cleaning, a quick inspection very easily without any hazards, since the body of the breaker is grounded, hence the name dead tank circuit breakers. Then we have some kind of hybrid circuit breakers, which basically it's a combination of both AIS and GIS systems. These kind of circuit breakers have both the compactness of GIS systems, for example, for their disconnectors, some earthing systems, and the, I would say, cost effectiveness of the non-GIS or AIS systems. Then we have the full GIS, basically gas insulated switchgear, or some people might refer to it as gas insulated substation. This GIS systems contain not only the circuit breaker, but all the switching components, for example, earth switches, isolators or disconnectors, containing the bus bar itself, and also the measurement equipment like the CT, VT, and the circuit breaker itself. And these GIS systems are not only in high voltage substation, as some people might think so, but they are also available in medium voltage installations or distribution systems. Their appearance there is quite rare compared to the high voltage, since their cost is much more, and the advantage that they give you is mainly with more compactness and smaller footprint of your substation. So these are a quick types, technologies over the year for circuit breakers, the medium voltage and high voltage, what are the main components, I would say, that we can find in all these types? So if I'm going to talk about circuit breaker components, I will divide it into, I would say, two types. We have main components that will be available in all these circuit breakers, and we will have some components that might available on some types of this breaker for some requirement for the breaker itself or for the power system to have that component in it. So for the main components, we have interrupters, and I will talk briefly about them in the next slide. Mechanisms, the mechanical parts that move the interrupter, control circuitry, and the insulation, whether it's for dead tank or a live tank or even GIS system. For N requirement, which I'm just going to mention them here, you might have, usually this is available in outdoor circuit breaker or AIS systems. You might have some capacitors for grading or shunt capacitors, and some resistors that work in pre-insertion or post-insertion. For our session today here, we are not going to talk about these unrequired components since they are very specialized and it might require some specialized testing. We'll talk about the general components that you might find for the interrupters and like the interrupter and mechanism and control circuitry. So starting with the interrupter main job is to interrupt or break the circuit during normal condition and during fault condition. Especially for the fault condition, your interrupter should be able to extinguish any arcing happening because of fault currents at different rating, different, I would say, fault current levels, different voltages. Usually, there will be one fixed contact and another contact that is moving. The mechanism will be moving this contact, and for requirement of fault clearance or extinguishing the arc, usually it will be operated at very, very high speed. There are many types and shapes of interrupters. I have some pictures just showing you here. For example, the one here is for a live tank circuit breaker, showing just briefly what components inside this interrupter. And the other one here is for a cross-sectional picture of a vacuum circuit breaker. You can see that the vacuum circuit breaker have a very short or very small gap between its two contacts, since it is not needed to have a very high gap because of our insulation media or lack of insulation media, because it's a vacuum interrupter. For SF6 circuit breaker, which are the most dominant in high voltage installation, usually you will have in each, the fixed and the arcing contact, you will have two types of contacts, a main contact and an arcing contact. And each one has a certain test to verify the condition of these two contacts. For our presentation today, to make it simple and to stay within our time frame, we'll be mainly focusing on the main contact rather than the arcing contact, since it does require, I would say, more specialized tests to check that arcing contacts. So just more information about these contacts and interrupters. And I would say high voltage and extra high voltage installation, you might have more than, we call it a number or more than one break per phase. So instead of using one interrupter only to break your fault or extinguish your arc, you have multiple breaks in series. So this is just the three pictures showing you what is, how does it look like for example, one break per phase, two break per phase, and four break per phase a live tank circuit breaker. Usually this will be available in live tank circuit breaker, in I would say GIS system or dead tank circuit breakers, multiple number of breaks is also existence, but usually from, I would say, testing point of view, you will not have access to be able to test each break individually. Usually they will be all in gas, for example, in GIS system, so you cannot really access them. Your circuit breaker might have them, but you can only access all the breaks at one time. Another component we have, which is very, very important, is the mechanism. The mechanism is the part where it operates the breaker. And usually it requires to be operated at very, very short time, usually in the tens of milliseconds, or I would say 1 cycle to 2 cycle of your rated power frequency. There are many technologies and many types of operating mechanism. Here I'm just mentioning some. For example, there is a spring type, which we basically storing the energy in a spring, either by expanding this spring or by pressing this spring to store this energy. Then we have the hydraulic method of mechanism. Basically, the hydraulic is using a pressured liquid and two, I would say, different cross-sectional area tanks to operate the mechanism. We have also the pneumatic operating mechanism types. Basically, it's a pressurized gas that will be released for the open and close operation. And last, we have the magnetic type, which are very rare to have and only for special types of circuit breaker, where they use magnetic fields to operate the breakers. What is the most common type of mechanism available worldwide is the spring mechanisms, because they require very less maintenance from the other types, but nonetheless there are still some hydraulic pneumatic available for some models and some vendors of these circuit breakers. So we said that the mechanism, it requires to store energy, usually a high amount of energy, and then release this energy to operate the circuit breaker, either for closing or for opening, in tens of milliseconds. So this energy must be stored correctly. So in case there is any leakage of this energy, depending on the mechanism type, the breaker should not be operated if the mechanism is not fully charged to give you the specified either trip time or close time. I would say the mechanism should be in locked position. You cannot, for example, open or close the breaker. And this is very important, because if your operating time is not what it should be or what is designed to do, and you are opening a circuit breaker on, for example, a short circuit current, there could be a possibility of a damage to your interrupters. And not only damage, in some cases, explosions even. The circuit breaker or the, for example, GIS system could explode if the operation is not done correctly. So there is a lot of, I would say, things built into the mechanism to protect against these type of conditions. For example, showing the position indicator, showing how many operation has been done as an operation counter. What is the state of the charge of the mechanism? It's fully charged, it's not fully charged, it's fully released. And there are some components that hold the mechanism after each operation ending, called dashpot, to absorb any excess energy after a successful open or close operation. Now, for usually high voltage, or I would say medium voltage, and to up to maybe sub transmission level the circuit breaker will usually have one mechanism that operates all three phases. We call this type of circuit breakers as gagged, or some people might call it common operated, where you have one mechanism to operate all three phases. And in, I would say, high voltage and extra high voltage, for each phase, they have one mechanism, which gives them the ability to operate only one phase, or I would say independent operation of each phase independently. These types of operations are usually only available in, I would say, high voltage or extra high voltage. And there is not only because of design that it is very big breaker, you have to have three mechanisms, but also from operation point of view. In case, for example, there is a single phase fault, they can just open that phase for a short duration, especially for transient fault, and they have an auto recloser that reclose this phase immediately after that fault clearance. It is very important when you are doing testing to know whether you have a gagged or a separate mechanism. But usually for separate mechanism, it's always most likely will be in the high voltage or extra high voltage level. Now, this mechanism is usually controlled, or it's controlled by usually a control circuitry. This control circuitry accept or receive the open and close commands from external devices like protection relays, control systems, RTUs, remote terminal units. And these control circuitry operate or release the mechanism using closing and opening coils. Could be usually having two opening coils and one closing coil. And also to add more protection against unwanted condition, we have usually an auxiliary contacts and limiter switch that will act as interlocks to avoid any wrong operation. Part of this control circuitry could be the circuit to, for example, charge a motor or motor charge to charge the, for example, spring mechanism or some types of mechanisms where this motor is controlled automatically by this control circuitry. Additional things could be, for example, alarms or condition checkers that will prevent any operation, for example, in GIS systems when you have the gas have a low pressure, or for example, the spring energy is low, it's not fully charged. All of this is available in the control circuitry. This is some pictures about some control circuitry from different breakers. Usually this control circuitry will have a diagram showing you where the, for example, the trip coil, where the close coil, where each limiting switch like alarms, cutouts, any, I would say, auxiliary contact that will prevent you circuit breaker indication, etc. from these things. So this is a quick introduction about some of the components in the circuit breaker that we are going to talk about. So it is very important to know your breaker so you can be able to test it. So know how many, for example, break per phase do you have. Know whether your breaker is, I would say, gagged, single mechanism, or three mechanism, gagged, or I would say independent mechanisms. What is the type of this mechanism? So you'll be able to handle it correctly and know, for example, where to connect in the control circuitry, etc. What is the insulation media, and this insulation media, what type of things you need to consider when you want to do testing? For example, in GIS environment, I will handle the test different than AIS or air insulated switchgear. Do you have any resistors or capacitors, pre-inserted resistors or post-insertion resistors, or any grading, any shunt capacitors? And how can I deal with these components? It is very important to know this to be able to test any type of circuit breaker. So now starting with the testing part, first you need to know what the common type of problems that you might face in circuit breakers. So according to a study done by Sigri, I believe this is in 2013 or 14, they found in this survey that about 30% or third of the problems that happen in circuit breaker are that they don't close in command, and about 15% that they do not open on command. So this kind of problem is usually related to, I would say, the mechanism, because the mechanism is the part which is responsible to open or close. Some of this could be also credited to the control circuitry, but usually across the years, the control circuitries has reached to a very robust level by the designers and vendors of circuit breakers. So usually the mechanical part, that either because of wear and tear, because of repeated operation, because of bad maintenance, could result in these problems. Other problems, for example, like breakdowns in insulation media, and for example, the poles or the ground system itself. And so huge part that we need to focus on is the operating mechanism. There is a lot of mechanical tests, I would say, that we need to do to make sure that these common of problems get decreased. According to the same study, the main components that become faulty is usually the operating mechanism, reaching to up to 70%. So it is very important to do all these mechanical tests, and I will explain what these mechanical tests that we have for the circuit breaker to make sure that it is operating correctly. So when we talk about type of test that we have in circuit breaker, I would say categorize it into three parts. I categorize it as basic tests that everyone should do regularly, even in just normal maintenance tests. These tests, we recommend you to do them, since they will give you most information about your breaker condition. There are some advanced tests, like the dynamic resistance measurement and the first trip test. And we have some special tests that is not for all types of circuit breakers, but only for certain types of circuit breakers. For example, pressure for air blast circuit breakers, vacuum check. This is for vacuum circuit breaker, where you check the vacuum inside the vacuum bottle or capsule. And SF6 purity. This is usually for GIS system and SF6 circuit breakers, where you can do that test. Not all of them is possible. So for the basic tests, this test might be, for many of you, are basics already known. We will talk about them, and in this training today, we will be doing or performing these 5 basic tests. The first test we will do is contact resistance, and then we will do a contact timing test, or basically some people just call it timing. There is a very, I would say, basic, but not usually done, which is test for the control circuitry. That's called minimum trip or minimum open voltage test. Check what is the minimum voltage required, by example, for our DC system, battery system, to operate the control circuitry and release the mechanism. Then we have some motion test or travel test. Basically, it's a test done on the mechanism, checking the mechanical part in it, how much movement, what speed, what each part of this movement is. And then we have, for the control circuitry, the operating coil current. whether it's a closed coil or open coil. We check the current through this coil, and we have a certain analysis to that test to check whether this test or this test is or this coil is not having any issue to it or not. So the first test I'm going to talk about in detail is the contact resistance test. Basically, we want to verify that there is a low contact resistance, usually in the range of micro ohm. Now, most tester to this micro ohm test, some people call it contact resistance, some people call it static resistance measurement, some people call it just micro ohm test, depending on the device itself. Usually, we use a high current to give us the accuracy to measure this micro ohm range. And according to the standards, IC and IEEE, for IEEE, the minimum test current should be 100 ampere DC. And for IC standard, it is minimum 50 ampere DC. Some standards even suggest that you inject, I would say, 10% of the rated current. The requirement of injecting high current is because of the very low ohmic value that the voltage measurement way, we usually use 4-wire measurement, 2 for currents and 2 for voltage. And the requirement for this is to eliminate any voltage drop across the 2 current wires that we have here. These 2 big cables, usually beefy cables, there will be a voltage drop on them. So in order to eliminate that, we connect 2 separate wires across the link itself to measure the contact resistance. One thing I would like to mention is that this 10% rated current, it is usually recommended for generator circuit breakers, where the rated current is in the thousands of amps, especially for big generators, for example, 6,000, 10,000 ampere. Now, in these cases, the 6,000, 10,000 ampere, the contact resistance itself, it's very, very low. It is in the, I would say, only single digit range, 1, 2, 3 micro ohm. So injecting 100, 200 ampere will not be enough. You need to inject very high current, let's say 500, even 600 ampere to test these conditions and get an accurate result. I myself have done this test on a generator circuit breaker. And that generator circuit breaker was, I would say, 6,000 amps, the rated current for it. I could not get a good reading when I used 100 or 200 ampere even. We had to use an instrument that can inject up to 600 ampere to get a consistent reading, a value that we can use or depend on for this test. So we have a live test set up for us today that we are going to connect and do the test and measure. I have with me our test equipment called DLRO. I am hooking it up to a circuit breaker ball, and we will conduct this test using this instrument. Basically, I have a circuit breaker with me here in the office, and I'm connecting to one of the balls to it to do this test. And as I mentioned earlier, we will have 2 or 4-wire measurement. 2 will be the current leads, where they will inject the current. I will inject 100 amps. And 2 cables or leads will be measuring the voltage to test or measure the voltage and get the resistance value. So we will be doing this test, and then we'll take a quick break, answering some questions that might you have, and then we'll continue with our session. So now I'm going to share my camera instead of my screen, and I will show you this in a live session. So the setup here with me, I have many devices connected. But today, or first, I will be focusing on the DLRO and the circuit breaker. So here with me, I have the circuit breaker. Hello, everyone, by the way. Here with me, I have the DLRO unit, and I have my circuit breaker as well. The DLRO unit, it is requiring us to connect two cable leads or current leads. They usually will be big, bulky leads to be able to carry that high current to do or conduct the test. And also, I will be having two small leads to measure my voltage across the link itself. So this test, it's very easily done. You just turn on the equipment by taking it either in the manual or automatic mode. For this knob, can you please zoom in on the instrument so everyone can see it? Yep. So I will just put it either in the manual or automated mode, which will basically start the test automatically whenever I connect all my leads, and will be showing here that when I have all my leads are connected. For example, if I remove this lead, it will show that I don't have all my leads connected properly. And then I can select the test current very easily, either from the predefined values like 10 amps or 50 amps or 100 amps. Also, I can define a predefined test current, for example, any value like say 75 amps or whatever, by selecting the ramp option here. Once I get any result, I can save this result inside the equipment, and then using our PowerDB software, I can create a report for these tests. So I will select the 100 amps, and I will just basically simply just click the test button since I have already everything hooked up. It will run the test automatically, ramping up, injecting the current, and then ramping down. The test parameters shown are very important. First, he's showing me the test current. It is, I selected 100 amps, but what it actually injected showing here is 101 amp. And then it's showing me how much measured voltage. For this 100 amp that I injected on this contact, I measured 3.2 millivolt. You can see that 100 amp only generated very small, I would say, voltage for me. So any noise in substation, any, I would say, very low ohmic value of contact resistance will struggle or make the test instrument struggle to get the voltage measurement correctly. And then dividing these two together, it showed me the micro ohm value, which is showing here as 31.6. I know that this breaker I'm having in the reference, or I would say factory acceptance testing, was showing 30 micro ohm. So depending on my temperature values here now, it is very accepted value. If I have a value that is quite high, let's say 40 micro ohm or 50 micro ohm, in that case, I will start to investigate what is the issue. Is my contacts fully closing together? Do I have any corrosion in my contacts? And all these other things. So it is very simple to conduct this test, very simple to see that. But you have to understand that for every type of circuit breaker, there are, I would say, different values. You need to check your reference value that you have from either the manufacturer of the breaker, from commissioning test, for example, and compare these values together. Or in case you don't have that, you can just compare other phases with each other to see if there is any difference between them. So, for example, in the range or in generator circuit breaker, as I mentioned to you, it will have only single digit, let's say 3, 4, 1, 2 micro ohm. And transmission and I would say medium voltage circuit breaker will usually have values in the tens of micro ohm. So this is, I would say, contact resistance. Additional things that you might need or might want to do in high voltage circuit breakers, you have the option to conduct what we call dual ground contact resistance test. Basically, in order to, I would say, accommodate some safety regulation, and also this is something we recommend, is to connect your test equipments on your circuit breaker when it's grounded from both sides of the contacts. This is very important when you are working in, I would say, energized substation, since in this case, any induction or any, I would say, capacitive coupling currents that flowing from adjacent live parts will not affect your results and measurement, and also will not create a hazard area for you. So it is always recommended to do these tests in, I would say, dual ground conditions. For the DLRO 100, we have some of the options in it is to conduct a dual ground test using our dual ground accessory and connecting, I would say, an additional earth clamp that will basically measure the current flowing through the earth during the test itself. So we recommend that, and you have the possibility to do that using our DLRO 100. Other equipment we have to do this test is also, we have the MOM or microometer. We have the Mueller. Each one have its own, I would say, specification, advantages, disadvantages. But that topic for another time. Now we will take a quick break to answer some questions and then start fresh again, continuing this testing session for timing and for minimum voltage test. Thank you, and I hope I see you in, I would say, 10 minutes. So, do you have any questions also with us?
Thank you for the presentation, Ali. Have some questions from the first one is, where do you connect the cables to get the measurement for contact resistant test?
Right. This question is asking of where do you connect the contact resistance or cables to the contact resistance test. Basically, it is to the pole itself. So I have a picture on the previous slide, if I can just show you very quickly. So I have the test lead showing here. I have one big test lead show for the current. a red one and a black one, showing here, and 2 leads for the voltage. Now, when you're doing the connection to the circuit breaker, each phase, basically what you need to make sure that the current leads far away, and then the voltage lead within them or inside the measured zone. So in order to show you this even correctly, I have the previous slides. This one showing you the 2 current leads. The bulky one is in the outer way, and the 2 voltage lead is inside the inner way. Now, it really depends on your circuit breaker where to connect them. For example, for live tanks, dead tanks, you will connect this outdoor very easily. You will not have a very big deal. You just have to isolate your breaker, earth it, and then you can do all your connection and do the test. But for, I would say, GIS systems, here will be a little bit tricky, where you need to connect to your earthing linkings. And from that, you will not only measure the breaker contact resistance, but all the path from your earth link to, I would say, the other end that you connect to. So for that, GIS systems, it is, I would say, a little bit tricky, and you need to make sure that the current you are injecting is not, for example, feeding into your CT and operating any protection, like example, any protection that is active, or any, for example, breaker failure, so you don't operate the whole bus bar.
Over to the next question. Thank you. So this question has 3 parts. What resistance is measured in dynamic resistance measurement? Is it the same contact resistance? What is the difference in contact resistance? Basic text.
All right. Thank you very much for this very wonderful question. So basically, dynamic and static, or what we call contact resistance, normal test, are exactly the same. Dynamic and contact resistance exactly the same. We both going to inject high current to measure the voltage and get the resistance value. But the difference is in the static, the breaker is in a closed position. We are not doing anything to it. But for dynamic resistance measurement, we are operating the breaker while we're doing the measurement. And the reason for that is that if you remember in one of the slides that I have explained, we have, especially in SF6 circuit breaker, we have 2 types of contacts, a main contact and an arcing contact. In the main contact, I can measure it easily or check it or verify that it is working correctly very easily with doing just normal contact and static resistance. But the arcing contact, it will be in parallel with this main contact. So if there's any problem to that arcing contact, I will not be able to see it. I have to remove, I would say, or absorb, or I would say, just delete the effect of this main contact and measure only this arcing contact. So how can I do that? I measure the contact resistance while the breaker is operating during that very short window where your breaker is only being connected through your arcing contacts. It is very important test for these arcing contacts, and it's not done alone. There is another test done usually in conjunction with it or in parallel with it, which is motion test. We will talk about that later on though.
Thank you, Ali. Over to the next question. In the illustrative drawing, how the black cables P1 and P2 are on the terminal and the red C1 and C2 are on the other. I think it needs correction. What do you say to that?
If I understand your question correctly, you are asking about the picture illustrated here. You're saying that the black cables are connected together and the red cables are connected together. This is just for polarity reason. The one thing I might think about why you are thinking like this is maybe basically as I would say the picture is a little bit small. It's not seen I would say very clearly, but I deliberately make the contact, or I would say current cables, a little bit far away from the voltage cables. They are not connected exactly at the same point, but the breaker I'm having here with me in the office is quite small, so there is not much space that I would say, create a huge difference between them. So maybe the picture is not showing it very clearly, but there is some, I would say, difference between the, I would say, the voltage and the current cables.
Thank you, Mr. Ali. So another question is, what is the best contact resistance value and limit?
Thank you for that question. I would say, and repeat this again, the best thing to do is to compare with what you have from the manufacturing test report or from the, I would say, commissioning report to see if there is any change happen in the resistance value. And usually these reports, depending on the manufacturer recommendation, will have the limits of what is acceptable or what is not acceptable as well.
So another question is, someone is asking, this device can be used to measure any kind of contact of breakers, joints, or bus bars eccentric?
Yes, you can measure breaker contacts, joints, bus bars, etc., all of them. And there is one, I would say, test mode that I did not mention or explain. It's called continuous injection. This is very important when you do, for example, for a long bus bar, you can inject across all this bus bar, and then just for the joint itself, you measure each joint separately using just the B1 and B2 leads very easily.
Okay, so next question is, can I perform contact resistant tests without isolating the breaker?
This usually it's not something you can do, but are you talking about medium voltage or high voltage circuit breaker? In medium voltage, you have to isolate the circuit breaker. It's usually very easy. You just rack it out of the cabinet. And for high voltage, you cannot really do that. You have to separate the breaker and do this test. So you have to isolate, open the breaker, isolate, connect earthing contacts. The one thing I would recommend you to do is to try to do dual ground measurement, where you will inject current in both. It will be going through both the main contact loop and also the earthing loop itself. And you will be measuring only the current flowing through the main contact, because you will connect an additional clamp through the earthing loop to subtract that current.
So we will take last question for this session, then we'll go on a break. So how much variation between contact resistance of each interrupter is accepted?
I don't have the value right now, but I can maybe share some examples with you from different manufacturers. So I will get back to you on this later on.
Thank you, everybody. We'll take a 10 minutes break, and please park your questions, and we will try to answer them whether on the next session or with privately.
Hello everyone, and welcome back again with us. Now we'll continue with our testing, continuing doing timing test and minimum trip voltage test. We'll do this test using a different setup, but before doing that, just a quick notes and knowledge about timing and trip test. Just adjust my camera a little bit. Okay. So when I talk about contact timing or timing test, basically, it is the time required for the breaker to complete or from the first pulse giving to the breaker open or close until the breaker contacts first separation or first touch, depending on the operation. So the sequence of these tests usually will have, I would say, close test, where you test the breaker, how much time it takes to close. Open, then we have some combination between this close and open time. We have CO, basically close and then immediately open. And this is what we call switch on to fault, or for others, they may refer to it as trip-free test. Then we have a close test, basically O, open, and then wait for a certain delay time, usually 300 milliseconds, and then close the breaker again. This will simulate an auto recloser function that may be utilized by protection systems or by, I would say, control systems. And then we have the combination of both, an auto reclose and trip free, where you have a fault consistent that you open for the first time, and then the auto recloser close, and then the fault is still existing, you have to open again immediately. So these are the 4 timing tests or sequence that we're going to do. We're going to check breaker synchronization, for example, between phase to phase. There are some special types of breakers that or require the trip or open or even close time for the 3 phases used in certain synchronization. An example of that, an application of capacitor bank. We have a capacitor bank, usually they like to open it or close it at the 0 crossing values of the voltage for each phase. And there are limits defined by the standard directly for this phase synchronization of these normal breakers shown here. Then you have, in case of multiple interrupters in your breaker, where you have, let's say, 2 or 3 or 4 or more, you have a phase synchronization where all the interrupters should operate with a very minimum value difference between them. Another test, this could be when you have some, I would say, pre-insisted resistance, main or resistor contact, where you measure the timing for the main contact and also for resistor contacts. This test is usually for circuit breakers that do have these resistor contacts. And last but not least, even the auxiliary contacts in the control circuitry, which is controlled by the breaker operation. Let's say a contact, for example, called ready to close 52A, that you can get indication of the breaker being open, ready to close, or another contact 52B, open, ready to, or I'm sorry, closed, ready to open. You can see how much lead and lag time from the actual main contact timing. So example of a connection, this is just an example of that, is to have your circuit breaker analyzer. In this case, I'm showing TM1800, our circuit breaker, high voltage and medium voltage circuit breaker analyzer, connecting timing leads. This is, in this case, 2 break pair phase timing leads, but usually the most majority will be 1 break pair phase timing lead, and you will have to connect to the control circuitry, connecting to the DC supply, to the open and close coil pulses. Usually you will be connecting with everything in series of your coil. For example, if you have many contacts in your coil that act as auxiliary contact, you will connect to them as well. So you, if the breaker is, for example, open, you can't open it. If it's closed, you cannot close it, and so on and so forth. So for this setup, I have, I would say, 2 tests that I'm planning to do. I'm going to do contact timing and minimum trip voltage. Basically, the minimum trip voltage test is similar to the contact timing, but I will be just changing one thing in the control circuitry. We'll talk about it later on, and see what is the reaction of the breaker in that case. And that test is very important to simulate some condition that might have in the substation. So I will be using the same breaker as I have before. And this breaker, in order to operate it, I have to give the close and open coil a DC supply. So I'm using B10E, our accessory as a power supply to circuit breaker testing. This B10E will be just giving DC, like a normal DC all the time. The DC rated value, or rated DC for this breaker, is 250 volt DC. So I'm just connecting that to my breaker. And also I'm using our TM1800 to connect to my control circuitry and to my timing leads. So I'm connecting and close and open command to my breaker, and I'm connecting 3 timing leads on the back of the breaker. I don't have all the connections shown here, but I will show them in a minute in the camera. One thing I would like to show, because it's on the back of the breaker, it will not be shown in the camera, is the connection from the back. Here you can see I have my leads. Just in my lead, I have my leads here. I have each pole, 2 sides of it. I'm connecting 2 leads, so 6 in total, and these leads all going back to my TM1800 for measuring the time. I have all the connection from the front, will be shown now in my camera view. So I'll be still sharing my screen so you can all focus on my camera. Right. Could you please just zoom in a little bit on all the setups so everything is cleared here? Okay, so I have here the TM1800. It's basically connecting 3 timing for phase A, phase B, and phase C, or RYB basically, and some control circuit. I have the trip and a close. I will show all the connection in the front screen of the device itself. And then I have here with me the B10E configured to deliver a voltage of 250 volt, 2949 here with me. This B10E is just giving this DC voltage without any operation. It's always giving this voltage. All the operation will be done by the TM1800. And then I have here my circuit breaker my connection to the control circuitry, the close and open pulses, and also the positive and negative. And also to make our life easier, I have connected the motor of the breaker to automatically charge the mechanism whenever I want to do testing for open or close operation. So going back to my TM1800, basically the TM is designed to be operated and also store all the results inside the device, showcase the analysis of the result, and also you can create a test plan for this testing. For our purpose today, and because of the low time limit or short time limit that we have, I will not go through every detail in the device, just the things that is important to know. So the first thing you need to know about the TM is that in the breaker list menu, you can create many breakers, give it a name, substation, ID, etc. I will not go through the process of creating that because it's very easy and it will be explained once you acquire any unit. So I will assume that we have created a breaker here. It's called ACB. This is my breaker, an air circuit breaker here showing. On this ACB, I can create tests, and then under the test, I can create some measurement. So I will begin a new test, either by using the knob to change the values or by using the soft buttons here. And I will give this test a name, let's say web or webinar. Now this test has been created. Under the test itself, I can see some operations already available for me. For example, here, close operation. I have close, open operation, and all. For example, open, open to. Any operation that is grayed out, meaning the detected condition of the breaker, it is in that position. So I cannot do open while the breaker is open, for example. I cannot do a close while the breaker is in the closed position. So the first operation I'm going to do is the open operation. To understand how the hookup and diagram for that lookup, I can just click, once I select the open, I can click on the analyzer view, and it will show me which channels from the top panel I should use to do this operation. So it will show me the close. This is where you connect the close and this part of the control. Then you have for the open, you can select it here. This is where the open, and then I have the timing channels. I have timing 1 for phase A, timing 1 for phase B, and timing 1 for phase C. In case I have a 2-break bare phase breaker, I will have the second channel of the timing enabled for me to connect to, but now I have only 1 break, so it's off. Now, in order to know more details about each connection, it's very simple. Just click on the close operation, for example, and there is this information diagram. I will click on it. It will show me how the connection should look like for each pole inside the device. Let me adjust the camera 1 second. Okay, so adjusted the camera very quickly. And so here it's showing me that I have, I would say 4 connection in this module. I have in, I have out, and I have 0 volt. Basically the in and out showing that I have to connect to my DC supply. So this is what I did. I connect to positive and negative of my DC supply. Unfortunately, you cannot see the negative. It is down below here. It's blocked by this keyboard here. And then the out, I will connect it to my coil itself. And you can see here, it's already mentioning that you have the auxiliary contact in series with the coil itself. So don't connect directly on the coil, but connect on all the auxiliary contact in series with the coil itself. Basically, what the control module will do is that whenever we start the test, it will connect the in, which is the positive, to the out internally, and will give a command to the closed coil to operate the breaker. If you want to know about the other connections, basically click on the open and click the I again, and we'll show you now the connection for the open. It's very similar to the closed condition, but you can see here it's mentioning the open coil and the A contact, basically the ready to close contact. For timing channels, I can click on the timing here for timing channel, and I click I, and it will show me the connection. There is this cable, it's been mentioning the part number for it. You will connect the timing cable, and then you will use only the black and the red leads from this cable to do this test. Basically, it's explaining everything to you, showing you what's the position, what type of module, what channel you are using, where the connection will be, and what is the measured quantity for this selected part. Because the team can do a lot of things, like example motion and analog transducer measurement, that's why it's showing all these kind of details for you. So now we are ready to do testing. The breaker is in the closed position. I will conduct an open position. Unfortunately, I cannot detect the breaker contact status right now because of the design of this breaker I'm having. So it will show some warning message. Don't worry about it. We will just go through it and do the test immediately. So I go back to the breaker list. I will select my open. I will click operate and measure. So in order to start the test, I will have select the open, and then I will turn this knob to operate and measure. It will show me a warning saying that the selected operation is not confirming with the detected status. I will just overwrite that and go ahead anyway. So I'll say okay. I'll do it again. It will show me another warning just to double check. I'll say okay, no problem, and start the operation. So now it will take some delay time, and then we'll start operating the breaker. I hope the sound of the breaker was heard to you. The breaker have opened. Can you just zoom out and show the breaker? I can show the status for the breaker itself. So the breaker is in the off position now, and we got all the results that we need inside our test equipment. So let me just go in the test screen and show you the result values that we got. So this is the, I would say, the analysis part now, where we got results. It's showing me a graph version here, that this graph showing you coil current, maybe some phases. The coil current, will look at that later on, but for now, just the timing, normal timing. So this is graph. You can see which value at which time the trip happened, but to make your life easier, you have the parameter section where it will show you the time for each phase. Phase A, phase B, and phase C. This open time is for the main contact. You still have other things that the time for them has been measured. For example, it will show an open time for the whole breaker, and basically this time indicate the longest time by any of these three phases, which is 23.5 milliseconds. And then we have some difference between the phases. It's showing here 0.6, it's calculated automatically for you. Also showing you the time for auxiliary contacts when they close and open. For this open operation, we are only checking the A contact. It's opening at 88 millisecond. And additional information about the coil current and also the control voltage during the operation. That will be very important when we conduct the second test, minimum voltage test. So this graph shown here, I can adjust it to my needs using the graph layout tool. Basically shift it around, adjusting the scale for any value, changing the color of each curve or each parameter as I like and as I need. And then after all, I can just print the result shown to me as a report, the parameters, and I can either print them from the printer inbuilt in the device or save them as a PDF file to be exported later on from the device itself. Now let's do an close operation. So I'll click out. I have now a measurement in the open operation. I'll click on the close and do another operation. I can double check my connection again in the hookup and diagram. If I click it, it will take me to analyzer view. It's basically the same connection. I don't have to change anything, but in case an operation that I have defined require an additional things, I will have to adjust these things in this analyzer view. And this will be required for us when we do travel and motion test. But for now, it will not be required. So the breaker is opened. I can just put it in the close position. Right. So now we did a close operation. The breaker is opened, and then we closed it. And to check this result, I will zoom in a little bit. Now I have my opening, or then being in the closed position. I can check the parameters to see my close time, which is 52. Basically, it was, I believe, 50 milliseconds. So there is a quick or additional delay of 2 to something milliseconds, which is okay for us. It's not a big deal. This is still within our specification for this breaker. Can also generate a report for these graphs as well. Now, this operation of the breaker, it is done for this kind of breaker only for close and open operation. But for any breakers in the medium and high voltage, you will also require to do, I would say, the other sequences like open, close, close, open, and open, close, open. Due to the short time that we have, we will not be doing these, but they will be showing similar way of operation where you will connect, you will measure, and the control will automatically generate the pulses required for this kind of operations. So now continuing to the second test that we have, I will share my screen again. And talk about minimum open voltage. Basically, it's to verify that the breaker will operate at the minimum voltage, meaning what minimum voltage? The minimum voltage of the control circuitry. This is very important because all of these control circuitry, or most of the time, they will be connected to a battery system. So when in case you are working in an outage and you have, or you need to operate these breakers, in low charge state, when the voltage starts to drop, once the batteries drain their charge, you need to make sure that the breaker operates at least according to IEC standard in these rated values. So the rated value for closed operation is 85% of the rated operating voltage. So for 250 volt, it will be 85. I believe 1215 or 12 something volt. For open operation, however, since it's very important to be able to open the breaker, we need at least a minimum value of 70%. But the thing is, for this test, it is not only doing whether it's tripped or opened or closed or only that. You have to as well check that the breaker will actually trip within its respective time. So if I decrease the voltage, what will happen is that this control circuitry or tripping and closing coils, they will have less punch in releasing the mechanism. So the trip time or close time could be a little bit increased compared to the normal rated operation. And this is what we are going to do right now. Hence why the requirement of this B10E, basically I will use the same setup that we did now for the timing test, but instead of injecting the full 250 volt, I will be injecting 70% to do this open operation. I'll inject only 175 volt from my B10E and measure what the trip time is. So I will open my camera again and we will continue this test live. Just stop the share. And zoom in on my B10E. Second. Oh. So here showing 250 volt. I will just decrease that voltage to a certain value. Let's say 175 is basically the 70%. And that's the importance of having a variable voltage or power supply. You can decrease the values to do this test. If you are using the DC supplied by the station, this is something you cannot control. That's why this test equipment is, or this variable power supply is required or important. And then, sorry. You can see now it's 175. Then I'm going to my TM and we'll do this test again. But before doing that, for my open operation, let me open my open operation. I will check how much is the time I'm having. Go back to my recording. If you remember, it was 23 something millisecond. So that was doing it at the rated voltage. So just to give you a better idea on this, I will zoom in. On the values here, it's showing 23 millisecond for my opening time. Now, when I decrease the voltage or the value of the DC supply to these trip and close coils, what will be the operating time? That's the question here. So we'll do another opening test. Basically, I'll select the open. I will operate again. Okay, operate. So breaker have operated. So now, if I go back to my parameters here, you will see that my trip time have increased actually from 25 to 29 milliseconds, which is still within the acceptable parameter or acceptable limits of this breaker. But this condition can and actually will happen if you are working in outage condition where your battery is supplying power to these trip and close coils. So in these cases, when this battery voltage start to drop, once they lose charge, you need to still be able to operate within an acceptable limit. So this test is very important when you want to do a close, when you want to do open operation, and the trip times or close times should stay in the acceptable limit range. So that concludes our second setup session for this test or for this testing, where we do timing test and we do I would say a minimum pickup voltage test. I can do it for a closing operation as well if you would like. Actually, let me just go ahead and quickly do that for the closing operation as well. Instead of 70%, I will be doing it at I would say 85%, since the close is rated for 85% of the rated voltage. I believe I just calculated very quickly. I believe it's 2125 volt. So increasing it to 212 volt. This is all right for us. And then go back to my TM1800. I'll check very quickly the result of the first at the rated voltage operation. The result is 52 or 51 millisecond for the close operation. So now we'll do it with the lower voltage rating. So I'll select the close. I will close the breaker. The breaker has operated. I'm expecting the time to be higher now, so we will see and check. So going back to the parameters, and wow, it is still, I would say, relatively the same, didn't change much, which is still a good thing. For the open operation, however, it only changed by a few milliseconds. So both my close and open operation during, I would say, lower or minimum voltage requirement are working very correctly. So now I will be taking questions again and answering any question that you might have. And we'll go to another, I would say, 10 to 15 minute break so we can start for the next session.
For the presentation, Ali. So to answer questions, I think he was. There's a question by attendee. I think he was like asking the question while you were saying something. So he says, of course, but would this not be the case on the dead tanks, as on the dead tanks we have CTs around the phases, where we will be injecting a DC current to the contact resistance? Or is it just a matter that needs to be considered along with the manufacturers?
Thank you for that question. The case he is referring to is that in dead tank circuit breaker, we will usually have what they call a pushing attached CT in this dead tank. This to reduce the manufacturing cost and also make the footprint less, so you don't have an outside CT as well and all insulation towards it as well. So in this case, you still can do the contact resistance test for the CT. And also what I would mention to you is that this CT, you need to short it from the secondary side so it does not conduct current to the protection relay, for example, and maybe operate it by mistake or anything. Another condition that you might need to consider, and I think one of the questions before was asking about where do we demagnetize the core. I understand what he's meaning now is that in case of this condition, when you inject a DC current on the primary of the CT, basically will be magnetizing the core inside that CT. So the demagnetization of this core is usually require maybe an additional device to do that for the CT. Or you can just apply a small AC voltage on it for sometimes to demagnetize that core to it. So this is another condition when you are doing testing on the dead tanks, or I would say GIS systems. The CT, you can demagnetize it by using, I would say, some equipment that can do that, or you can just apply an AC to that CT secondary and it will be demagnetized with some time.
Thank you, Ali. Another question, are you going to speak about hydraulic mechanic in this course? Because I have a question related to the hydraulic nitrogen in the hydraulic system.
For the hydraulic and I would say pneumatic mechanisms, I did not, to be honest with you, prepare a lot of information regarding them. But one thing or another things to be mentioned here is that we have special accessories that can measure the pressure, for example, in a pneumatic system while conducting the test. So how much the pressure is dropping when you are conducting an open or close or a double operation, that you can attach to the TM and measure that simultaneously while you are doing the operation itself. So for that case, we have an accessory for that. You can do it. To be honest with you, in the region I am in, Middle East, I did not face a lot of breakers that have these types of mechanisms, so I don't have experience. But our factory in Sweden or manufacturing side, they have faced a lot of cases like that. So I would suggest to you to drop me an email. I can share my email on the chat, and I can contact the guys that can give you more details about this. So I'm sharing my email on the chat window. Can drop me an email and I can maybe discuss this further with you and our specialist team for this.
Okay, so another question from an attendee. What are the quenching media and circuit breaker?
You mean arc quenching media. So it really depends on the type of the circuit breaker. For vacuum circuit breaker, you have vacuum, basically nothing. You remove all the particles from the bottle itself, so there is no arc that will be forming. Maybe when the voltage is very high, any leftover particles might create some arc, or even the contact itself, when they wear out, I would say particles from their copper or wear out material will be conducting some current. But for vacuum, that's it. For most other circuit breakers, you will have usually SF6, pressurized SF6 media, where it's been released in the quenching area to quench the arcing. All the breakers, I believe, obsolete now, is using, for example, air blast. In this case, for air blast, the quenching mechanism is that they released a high pressurized air very, I would say violently, and usually that breaker has a very loud sound when operating. It's very loud. Use an air blast to make the, I would say, insulating media, which is air in that case, changing all the time so it can quench this arcing. Another insulating media is oil breakers, which kind of obsolete now. There are two types. You have bulk oil, where usually you'll see a very big tank that have the interrupter inside and a lot of oil inside to quench the arc. And that require really high maintenance for the bulk oil. And there are the minimum oil type, which require less maintenance than the bulk oil. But all of these breakers, the air blast and the minimum oil and bulk oil, have been replaced with SF6 types gases. Basically gas insulated breakers.
So we're going to take the last question for this session until we go for a break. Okay, so the question says, if two tests are done using two values, odd current, let's say 50A and 100A, is there any correction to be used to compare the two values of resistance?
So at 50 ampere or at 100 ampere, the difference is that the voltage being generated or being applied across this contact link, whether it's a contact or bus bar or joint, will be corresponding to the injected current. So the voltage will be double for 100 ampere compared to the 50 ampere. But the resistance value should not change. It will not be different. So the value itself will not change a lot. What the importance here to know is that the reason why we injected this high current, 50 ampere or 100 ampere, is that because of the test equipment of conducting this test, I have to inject this high current so I can generate this low voltage and be able to measure it and get the resistance value. Of course, the best thing is to compare a value injected at 50 ampere with a value you are testing at injected at 50 ampere, and 100 ampere with 100 ampere. It will be the best way, but it's not always possible to do that. Maybe the test equipment they use in the factory, it's much more accurate at 50 ampere than the test equipment you are doing it on the site. So on the site, you refer to injecting maybe higher current to get that same accuracy as the factory itself.
Thank you, everyone.
In general, I would say, or basically, it is not bad or a bad measurement that you get between 100 and 50 ampere.
Thank you, everyone, and thank you, Ali. We'll be taking 10 minutes break, and we'll be back with the other sessions. Thank you.
Hello, everyone, and welcome back with us. I know we took a little bit more than 10 minutes break, but we had many requests from many participants to give some time for prayer time. So we extended this break by an additional 5 minutes. So hopefully everyone with us is still, and we can continue to our session here. So continuing on, we will do travel test, or basically what's called motion test. But this is a question that I always faced whenever I talk about a travel test, or when I recommend someone to do a travel test. They ask me why. Why do we need to do this test? It is difficult. It is not applicable for us. It's not doable for us. I understand all of these concerns, so that's why I prepared this slide specifically for this. Travel test is applied by standard. It is a standard test that is required to do not only in the manufacturing site, but also during service and in substation and in site as well. And the reason why the standard is doing that is because when you do timing test only, it doesn't tell the whole story. I actually have a presentation, or I say webinar, that I have conducted earlier. You might find it in our recording, in Megger.com website, talking specifically about motion and travel test. Maybe our team can share the link later on for you. It will give you more information about your breaker. And there are some conditions to your breaker that timing test alone will not give you. Because remember, timing test is only when the first separation of the contacts happen, or when the first touch of the contact happen. What happened before and after, timing test does not tell you, motion test does. And also give you the possibility to trend, for anyone who like to do trending for the circuit breaker, the possibility to trend the result of a motion or travel test. So what are the things or the parameters that we consider from travel test? It's basically, there are some number of parameters. The first one is called the stroke. Basically, how much in millimeter, or whatever the unit you are using for conducting this test, the interrupters of the breaker is moving. And usually this stroke will tell you whether the breaker or the interrupter has traveled the full length or not. This is the thing we call stroke. In case of any over travel or under travel to the full specified value, we can check it in the under travel parameter. At which value the contact have fully closed or fully opened, we can see with the penetration or gap test. Basically, all of these tests is done at once. It's just the parameters you will get from them. Also, I can calculate the velocity or speed. And if there is any bouncing at the end of the operation, I can see it from the rebound parameter. This graph shows you an example of a motion test, how the different parameters will look like. So starting from the open position, the value will become low, and then will go high, up, and the full length from the closed position to the open position, we call it stroke. The value when you have an additional travel from the final position, we call it over travel, for example. If there is any bouncing or rebound, we can see it in the damping zones. Also, the speed can be calculated. Since you have the distance, you have the time, you can just basically take 2 points from the distance or the motion curve and get the speed calculation, which is something very, very important, that the breaker is moving in certain speed value. Now, how can I capture or measure this motion? In order to do that, you have to understand how the mechanism is operating. This slide will explain it very easily for you. Apologize about this. Seems that my computer is not responding. Let's just give it 1 minute. Yep. All right. So in this slide, here I have, I would say, a quick brief idea about how motion is captured. So motion inside circuit breaker mechanism, they come in two ways. You either have a linear motion where they go in and out, or you have an angular motion. I would say a gear that is rotating to change this linear interrupter from open to close or close to open position, etc. Now, these types of motion, the linear motion or the angular motion, we capture them using something called transducer. Basically, what this transducer does is that it measures this motion, usually attach it to the, I would say, the mechanism of the breaker, and will capture this motion either in millimeter in linear motion or in degree and angular motion, and report back to the test equipment during the operation. So when I click open, or when I start an open operation test, the timing can be measured, and also the motion can be measured simultaneously at the same time from the test equipment. Now, these transducers usually come in ready-made kits that you can mount to different types of circuit breakers. So this is an example of some kits that we have to be connected. All of this is a linear transducers that you can connect, a linear bar that can measure the motion while it's moving, and will give it back to the test equipment in either millivolt or milliamps or even a resistive way. This is another kits that we have. That is an angular transducer mounting kit. So the kit itself, the transducer, is only this small black part here that you can see. While all the other adapters and other, I would say, mounting accessory will be used to be mounted to different types of mechanisms, breakers, gears that you type into. And usually these things allow you to, I would say, use a universal transducer for all or many types of breakers. So I have some pictures here showing some linear and some angular transducer. I have a transducer with me here in the office. I will be just giving you a quick brief idea about it, how does it operate and how does it mount on a circuit breaker. So this is a picture of a bulk oil breaker with direct linear measurement. You can see the transducer there. This transducer is zoomed in here. The transducer is connected to the interrupter directly to measure how much is moving in and out during open and close operation. This another picture of angular transducer that's been mounted to, I believe this is GIS systems. You can see the pipes behind it. So this transducer, the transducer is here. transducer is shown here. And this small part, and all of the other accessories just to hold that transducer to shake it from moving. This is another breaker. They have two pictures of it. This is the picture from the front, and this is the picture from below. You can see the transducer here. It is attached using a certain type of accessory, depending on the breaker, how it's manufactured, and how can you mount to that. The main thing here is you have your own breaker. It might have some types of attachment. The manufacturer can help you or can recommend for you which type of transducer and mounting kit that could work, and we can also help you with that from our experience as well. So it is not something difficult to do, mounting a transducer. Actually, I will explain or demonstrate how a full assembly of an angular transducer is done now by opening my camera and showcase that for you. So I have transducer here with me. And I will be playing around with it a little bit just to show you how does it work. So the transducer itself, an angular transducer, is only this part. All the rest is just helping hands and assisting. So for example, if I have mechanism in one way or one part, I can just attach this leg here into the mechanism compartment, for example. I can rotate it for different places, different issues, all of that. And just release this and rotate this as I like, if I want. And just the hands like this. Now it's locked in, for example. Now I can move it like this. And this is from the side. You can see the transducer here. This is transducer. I'll connect a cable to it from the back to the TM, for example, to capture the motion. And then I will attach the rotating part here, where you can see it is rotating. Attach this using a small adapter to the what we call the mechanism part, as I have shown in the pictures. So it is really simple. You just need to know where to mount. Usually you will find a part that is rotating like this, so you can connect to it and do the connection. You have to hold it tight. That's why the helping hand here is now a bit tight, so you don't have any jiggle or anything like that. And then you mount it from the front, and you connect the electrical connection from the back to your TM to do this test. So this one type of transducer. We have many other types for mounting, like linear transducers. We have some types for special breakers as well. For example, we have a specific transducer for some ABB mechanisms, HMB and AHMA, where we can do this test as well. So this is just a quick demonstration of the transducer, how I would say it can be a mount. Unfortunately, I don't have a transducer with me here, or a mechanism that I can mount to it. So I will just run with some, I would say, simulated values, just to show you how motion measurement will look like inside my test kit or test equipment. So let me share back my screen and continue with our testing. So for motion test and later on also for the using the same setup coil current test, I will be using our breaker simulator. It's called BRS 503. It's just a simulator of a breaker that we can do timing and a travel test at the same time in it. And also it has an inbuilt transducer. The transducer is already built into this simulator. So I just connect the interface. And also with my TM1800, I can measure the time, the motion, and also the control circuit currents and voltages at the same time during open or close operation. The connection is as shown here. I will be connecting my control, close or trip, both of them to my control circuits here in the simulator. And also I will be connecting an analog channel, which is required for analog type transducers. We have some digital type transducer as well, to the motion inbuilt, and also the timing leads, phase A, phase B, phase C, as we did for the ACB breaker that I have previously. So let's open the camera again and start doing some testing. So now I have everything connected. We did this all connection during the what they call the break, just to save time for us. So I have all the connection done. Let's go back to our, let me just delete that one. I have already created a test file and we are ready to conduct this testing. So in order to do testing with motion transducer or any transducer with our TM1800 or 1700, you need to define what that transducer is. That's why you have here the option hookup and diagram. So let me zoom in more to give you a picture about it. So here you have hookup diagram and a transducer when I select close operation. So when I click on this, it's still using similar channels as before, close, open. I will have my timing channels, and I have something additional here to be linear transducer, linear sim, CB sim. Basically, this is the transducer I'm using. So depending on which transducer that you have connected, depending on your mechanism, you can select this from list of transducers. So select a transducer, click select, and the list will be defined here for you. We have different models. Most of them are inbuilt. In case it is not built for you or inbuilt here, you can still add any transducer that can interface with us in the transducer link and add for angular or for motion transducer, you can add this transducer yourself and define the values for them and all the calibration for that as well. So back to the analyzer view. For us, I am defining my transducer as CB simulator, which I call just CB sim. It's selected here. So I am now ready to start doing testing. Breaker list. The breaker is in the open position. I will just start the operation by just operating and measure. It will give me the first check warning, no problem. As you can see, the result is showing here now. From the result, I can see here I have some auxiliary contacts. Let me zoom in more. So what you can see is here. So I have auxiliary contacts values shown here. I have the main contacts, phase red, phase yellow, phase blue, and I have my coil current, which we'll talk about later on. And last here, I have my motion measurement. Now the motion and the coil current both share the same color, so I can easily just go to graph layout and make the motion different color. Let's say, for example, a black, or let's go black. I like black. Something different, let's say purple. Now my motion is showing you here the curve for the motion, starting from the open position, going up until the closed position. You can see there is a small bump and then go down again and back to, I see some comments here indicating that the color is not very clear. So let me change it to something more appropriate. Let's say white. Right now, I hope it's coming in better now. Now you can see this motion starting from open position going into the closed position. You can see there is some, I would say, over trouble here. The full stroke is around 6 point something millimeter. All of these parameters will be shown in the parameter section. I can click just parameters. I can see in addition to times, so I have my main time, phase A, phase B, and phase C. I also have some parameters for the measurement, for the motion. So down, I can just go down. Here you have stroke showing 6.7 millimeter. I have the speed, the closest speed is 0.4 meter per second. Basically, it's taking the 2 points from the stroke or the motion to calculate this value. You can calculate different speeds based on different requirements as well. You have an over trouble of 0.3 millimeter, which is good for us. We have no bouncing at the end, basically rebound. So all our motion values are within limit, I would say. Let's do now an open operation. So I'll go back, select open, and then operate the breaker. Since you already selected the transducer and close, you don't have to select it again in the open. Right now, I'm going back to our measurement as well. So I'm going to make this motion to be yellow again. 1 second. You can see the motion characteristic or curve is showing that it's going from the closed position. Then while it's opening the breaker, it is going down to the open position. And there is a small over trouble here at the end we can see as well. So if I go to the parameter section, go to parameters related to the motion, which is basically these, the stroke, open speed, over trouble, and rebound. You can see that the values shown for the stroke, 6.7 for the speed. The speed operation for the open, operation is faster than the closed operation, which is expected since the open operation is more important than the closed. So it should open faster. I have 0.2 over trouble, which is basically nothing, and 0 rebound. So basically during timing test, I can do a motion test as well at the same time. The next test we have is coil current. Using the same two measurements that we have, we will talk about coil current. But before doing that, I would like just to give a quick explanation of what we are doing for the coil current test for the control circuitry. So I'll share my screen again. So coil current trace. Basically, when you are opening or closing a circuit breaker, you're basically energizing a coil. This coil have inside it, I would say, a plunger. That this plunger will operate a latch, a mechanical latch, to, for example, your mechanism. In this case, I'm showing a spring mechanism, but for the other mechanism, it will be something similar. So when you are charging or applying a DC current, for example, this is specific to DC coils. When you're applying DC voltage to any coil or any inductor, what will happen is that this inductor will start from zero current, charging up until it reaches steady state of short circuit. So coil current is the same. I'm sorry, open and closed current is the same as well. But the thing here is that there is a moving part that will, I would say, give it a unique characteristic of this coil current. This moving part is the plunger. When you first energize the coil, it will start from zero, going up, going up. During this, I would say the breaker is in the open position, and just want to show the presenter that I'm having here. It's not working correctly. 1 second. So this coil current, once you start energizing this coil, it will start moving this plunger. This plunger will hit the latch, and once this plunger hit the latch, what happens is that the coil current will drop. This drop is because of the force applied by this strip latch on the plunger. Now, once this plunger starts hitting the coil or the latch, it will start to drop. And once it reaches final position at point number 5, the mechanical energy stored in this mechanism will start to release and operate the breaker. So now the coil reach, I would say, a steady state value, or I would say the plunger reach a stop position. The current will charge again to its final position. All of this duration, now my mechanism is moving. Now this mechanism, when it's moved, it will operate the breaker, and at the same time it will operate the auxiliary contacts, the ready to open contact. This contact, when it operates, it will de-energize the coil itself, and the plunger will retract to its rest position, and the current thus drop to zero. So in order to explain this even further for you, I have a quick animation. I hope the screen, sharing that screen will not create any issue for that animation. This quick animation will just give you a brief idea of what's happening. So when I give an open command to my coil, what will happen is that the coil will be energized and the current will start flowing through that coil. Once that current starts flowing, fortunately, it seems that it's not showing the, I would say, the animation very easily. That plunger will start to move and release that trip latch. Once it hits stop, the current will reach a certain value and then will continue to release the mechanism, and the current will start moving to the maximum value it can reach. Once the breaker is fully open, the auxiliary contact will open and the coil current will drop to zero. Now, the coil current measurement, you don't have to do any additional things. It's already been measured directly from our control module. So the same connection you do for the control, you gain the coil current as well from it. So there is no additional connection required. It's already by default coming in with you. In order to analyze this value, it's very simple. You will just compare between previous measurements that you have. For example, for this reference value, and compare it with a new one. If, for example, the first jump, basically defined by A here, it is giving you, I would say, a big shift between the first drop and the new measurement, means that you have a problem with your coil. If, however, the shift is in the B1 here, let's say that the A shift is almost zero, and you have a B shift here, means that there is no problem with your coil, but however, you have a problem with your mechanism. This is very important when you are doing timing test. Let's say you did timing test today and it was 25 milliseconds, and you did timing test after 1 year and the time was 30 milliseconds. You want to know where this delay came from. Is it from the coil or is it from the mechanism? Since the coil will operate the mechanism. So by looking at the coil current, you can find these values or the issues from here or from there. Now, let's see this in our test that we have conducted in the TM1800. Share my camera again. So here you can see the coil current. There is two jumps here, jump 1 and jump 2. Now, there is a very nice feature you can use in the TM1800, the analyzer tool. Is basically go to, I would say, advanced analyzer. So in order to see this very accurately, I will go back out. The system setting here, I can just select to use the advanced analyzer tool, hardware, advanced. Now I'm going to open the same measurement we were seeing before. View. And now the measurement is having, I would say, more advanced view for it. It's basically like a VC software. So it's very advanced for example, you can have cursors, you can have a lot of things. So I can just adjust a little bit like this. I have two cursors that I can, for example, put at the start of the operation. And the other one, the second one, at the first jump, end of jump. So this is showing me that the coil took almost, I would say, 32 milliseconds to reach, or the plunger to reach its final stop. Then another, I would say, if I took the secondary cell for the final operation, another 31 millisecond to the mechanism to do its part of opening or closing the breaker. In this case, closing the breaker. So if I did this measurement now, and after 1 year I did another measurement, I can compare these measurements directly on top of each other using the compare function available for me in the top here. So I can compare within test, or I can compare between tests, where I select another file and I put it on top of this and just compare the two coil currents at the same time. Can even make it bigger, for example, this coil current. And just hide everything else and just focus on my coil current for this, for example. So my coil current is now shown here. So this, I would say, quick verification can really tell me whether I have a problem with my coil or whether I have a problem with my mechanism. So coil current test is one of the, I would say, basic tests that is recommended always to look at it when you have any problem with timing test. If timing test is fine, then you don't really have to look at coil current that much. So this concludes our, I would say, live part. And would like to thank you all for joining us in this, I would say, quite long session for us today. Before we end, I will just quickly show you some of our innovations and some of the tests equipments that we have that can fit your needs. So Megger have been developing test equipment since a very long time, especially for circuit breaker. We have a long time history track that I would say really gave us a lot of experience in circuit breaker testing. We've been doing it since a very long time, previously known as Programma, now under a Megger umbrella. We have many test equipments that is out there. Some of them date to, I would say, 80s, that is still working today. For our solution that we provide today, now presently, we have the low resistance ohm meters or micro ohm meters, the DLRO, Muehlner. We have the circuit breaker analyzers, EGEL, TM1700s and TM1800. And also for vacuum interrupter checker, this is basically a hybrid test. We have the VADAR unit that can do that. In addition to that, our multifunctional tester, TRAX, can do both contact resistance and timing from the same unit itself. Among other things like a transformer testing, I would say CT testing, VT, or primary injection in general. And also we have, I would say, quite the range on the contact resistance. For example, we have this small unit called MOM2. It's a handheld device that uses supercapacitor technology to inject high current for short amount of duration. It's very, very, I would say, smart device that can use only a small box, a handheld box, to inject high current for this test. If you require more details on testing circuit breakers, we have a complete testing guide that can give you all the recommended tests, failure points, all details about test equipments called Circuit Breaker Testing Guide. I have the link here, and we will share the link in the chat as well for anyone who would like to see that. Now we will take and answer any question that's been asked during all this session, and any additional question from previous sessions that we did not answer.
Thank you, Hadi, for the informative presentation. So we'll take the first question. Last question related to the timing, he's saying. How can we test timing for GIC circuit breakers?
Okay. So for GIS circuit breaker, we can do the timing usually from the what we call the earthing links. You have in GIS system basically a whole substation in gas. So you have your bus bar, you have your disconnector isolators, you have your earth switches, and you have your circuit breaker, and among other things like your CT and VT and cable termination as well. So the GIS system, you cannot access the circuit breaker directly to connect directly on it. There is the only way is through connecting your earth switch for both sides, and then the earth link that link the switch to the earthing system itself. It's usually located outside the GIS to give you, I would say, an access. So you can use this earth link to do this timing test. The only thing I would like to mention is that it is important to do this in dual ground, especially for energized substation. So we have a solution for dual ground testing. Let me just share that slide. I believe I forget to mention that slide previously. Yep, this one. So for dual ground testing, whether you have a GIS or I would say a dead tank or a live tank circuit breaker, we have a method using a high frequency source that will inject a high frequency signal across the whole loop and measure the response of that loop. And using a Knapper method, we can detect open and close position. This can be done when you have a single ground or when you have dual ground. So that's why it's called dual ground testing. The method we are using is called DCM, dynamic capacitance measurement. Basically, whenever the circuit change, either open or close, the circuit will change. That's seen by this DCM method. We will be able to detect open or close method, open or close status, and very, very accurately. This method has been developed by Megger since, I believe, 2005. So it's been in the making a long time and have proven, I would say, withstand time for it from a very long time. So it's very, I would say, valid method of doing dual ground testing, which could be very important for GIS systems.
Okay, so next question. Is VIDAR test a routine recommended test?
VIDAR test, what he's referring to in this question is that called, I believe, vacuum interrupter dielectric absorption test, or basically a high bot test to the vacuum bottle. Now, in vacuum circuit breakers, the interrupters is located inside a vacuum enclosure or vacuum capsule or bottle, whatever you want to call it. This vacuum, it is not, I would say, or I would say the best way to test the insulation integrity is to apply high bot. You can do insulation resistance test or Megger test, usually referred to. But the best way is to do high bot. Why? Because only breakdowns could be seen or shown when you increase the voltage up to, I would say, the withstand voltage. The particles, leaked particles inside this bottle can create some leakage currents. So I would recommend this test as to be done routinely using our VIDAR tester, since It is designed specifically for, I would say, doing a vacuum interrupter checks. I actually have a quick video. Time allows, I believe we still have some time to showcase that. So let me stop sharing my screen and maybe share that video with you guys. Stop the video and share. So I'm going to share my screen now again. Basically, I have a video specifically to the VDR test. This video will explain how this VDR test is done and how does it look like.
Producing high-quality test instrumentation for over 100 years. VDAR presents a superior alternative to AC high-pot testing. Traditional AC equipment is more than 10 times the weight of VDAR. Insulation integrity test is recommended by the manufacturers of circuit breakers and well documented in international test standards such as IEC and IEEE. VDAR has a user-friendly pass-fail test procedure where a light indicates the test result. The procedure avoids unneeded misinterpretations based on normal fluctuations of stray current. Those are mostly due to test environment variables, such as relative humidity or polluted surfaces of the test object. At a fault indication, just confirm it by a renewed test at reversed polarity. A typical test of a vacuum circuit breaker follows a simple sequence. Make sure the circuit breaker is secured and safe to work upon. Put it in the open position. Ground both test instruments and test object to the same point. Apply HV test leads across the first phase vacuum bottle. Set the test voltage selection switch of VDAR to the voltage nearest to the desired test voltage given in the circuit breaker's manufacturer's specification. Twist the double command and note the test result. You can now repeat the sequence for phase 2 and 3.
Yeah, so that was a quick video about the VDR system. Basically, it's a very simple to use system. You just connect to the breaker or to the vacuum circuit breaker specifically, and then you make it open, ground, just turn two knobs together and run the test. Unfortunately, I don't have a vacuum bottle with me here or the VDR itself to demonstrate that for you. But basically, it's very simple device to be done and simple device to be used, really. So do we have any additional questions?
Yes, we do. Can we do coil current analysis to record the current signature of the coil when the breaker is operated?
We just actually did that right now. When we are opening or closing, just stop sharing my screen 1 second. So what we did previously is for the coil current analysis, we record the current while we are opening or closing the breaker. And during that record, I can, as I mentioned from the analysis that we did, we can see whether I have a problem with my coil or with my mechanism. This recording value, if you don't have it previously from the manufacturer or from the commissioning test, you can, for example, do it now. If your timing test is okay, there's no problem with it, you can do it now and use it as a reference for the future. Or you can go to, I would say, sister circuit breaker, similar circuit breaker, take the measurement out of that and use it as a reference for the other. But please make sure that it is operating correctly, the timing test for it, everything, motion is working correctly. But by default, from what I see, all manufacturers always, I would say, provide the coil current, since it's a very simple test, and most test equipment by us or others do provide the coil current measurement.
Thank you, Mr. Ali. I think I'm going to give you a break for a minute and allow the question for Mr. Hamid. Mr. Hamid, this question is for you. Where should I attach the motion transducer?
Follow the circuit breaker manufacturer recommendation. If the above is missing, you should choose a point in which the motion of the movement contact, as close as possible, is reflected. The point could have a linear or a rotary movement, and it could be located in the operating mechanism or in a gear case close to the breaker board. In other words, it is depend on your circuit breakers and your system.
Thank you, Mr. Hamid.
Just to add, according to this question as well, we are here always to provide you with any knowledge you require for motion test. So in case anyone who are, I would say, intimidated by doing motion test or feel doesn't have the required information by that, we are here to help you do this. So please contact me. I dropped my email in the chat. Probably should do it again. And I can help you with maybe locating where to mount. And also we can maybe get the manufacturer on loop with us to recommend where he do this, because I know all manufacturers do motion test in the factory since it's required by standard. So they can recommend for us where to connect. Some, I would say, some circuit breakers, usually in medium voltage, it will be a little bit difficult to allocate this position, either because it's very small or compact, or maybe it's internal, you cannot access to it. In this case, not doing timing or travel test is okay for that. But in breakers where you can do, please do it. And we are here to provide help for you for that.
So I believe we can conclude our session today. I hope you enjoyed it and it was informative. If you need further clarifications on each point was mentioned, please feel free to contact Mr. Ali Hussein at any time. And also, we will share the recording within the next 2 days. And yes, thank you, everyone. Thank you for joining. And see you in the next webinars.
Thank you, everyone, for joining us. It was really my pleasure. Thanks to Hamid and Ali Azam for helping me prepare this, I would say, long session. It's first of many coming in the future, hopefully. I prefer to always do, I would say, a practical session, since it gives more value than just a theoretical one. So if you like this, please, in the feedback form, give us a good rating so we can continue everyone If you didn't like it or you feel there could be some improvement, also drop a comment in there. Your comments are very important for us. I read them and I build upon them. Thank you all, and goodbye.